So thank you very much for your kind invitation. I very much enjoyed the talk that I'm going to present. So I will be very happy to share this with you. So the title of my talk is AdS distance conjecture, and actually it started out. So as Dita pointed out, I'm sharing my personal email with everyone. So it started out last year when Miguel kindly invited me to give a summary, some kind of a review talk at Swamplandia, very nice Swamplandia last year at Madrid. And he asked me to give some kind of overview about the connection between swampland and holography and what's interesting and what has been done, etc. So this was a very nice opportunity for me to sort of think about various swampland conjecture in the context of AdS, CFT, and holography. So this is the first page of my talk. And I talked about a variety of things like my previous work with Daniel Harrow about the absence of global symmetry. But most importantly, there is a very important work by Eric Perlmutter, Leonardo, and Qumran, and Irene about CFT distance conjecture. It gave me very nice opportunity to study this paper. And there is also very nice work by Asmund Fogstedt about the constraint on potential in the context of AdS CFT, which I do not have time to talk today. But so today's talk is about this AdS CFT, the distance conjecture in the context of AdS CFT correspondence. And so everyone knows the AdS CFT correspondence, but you can use this as a first principle of quantum gravity and use that to try to identify and derive low energy constraint on gravity. So this is the idea of using AdS CFT to understand the swampland condition. And so this is what Aaron pointed out to us a few years ago, that perhaps the earliest swampland condition was proposed by Albert Einstein in his autobiographical note. And in this, there's actually a nice chapter in which he explains the notion of natural unit. And he said that if you express laws of physics in terms of natural unit, then only dimensionless constants occur in these basic equations in physics. And then he says, concerning such, I would like to state a theorem, which at present cannot be based upon anything more than upon the faith in the simplicity, namely intelligibility of nature, that there are no arbitrary constants of this kind. So you can actually formalize this statement in the modern language by saying that every parameter in quantum gravity, somebody is writing on my, somebody is doing something on my screen. There was a name on it. Who is Schunar? Whoever doing this, could you stop doing this? Every parameter in quantum gravity is an expectation value of dynamical field and can be varied by changing its expectation value. So this can be this is something you can actually prove in the context of AdS CFT correspondence. So suppose there is a gravitational theory with a continuous parameter lambda, like it is assumed in this conjecture. Then by AdS CFT, there is a corresponding parameter in CFT. So I parameterize a CFT Lagrangian density in terms of the same lambda. But then suppose I deform this parameter, well, so there must be some exactly marginal operator which generates this deformation. But then according to AdS CFT dictionary, if you have exactly marginal operator, there must be a corresponding massless scalar particle in the bulk gravity theory such that this scalar field expectation value determines the boundary condition. That the lambda determines the boundary condition of this scalar field. So you can say that parameter lambda is an expectation value of some scalar field in AdS, and this is exactly what this conjecture zero says. So you can actually prove this statement in the context of AdS CFT correspondence, except that actually the assumption that whenever you have a continuous parameter, there is a corresponding exactly marginal operator is actually a conjecture about conformal field theory, and it actually requires a proof. And so I pointed this out in my summary talk at the Strings 2022. But now actually we are almost proving it with Kyota Komatsu, Yu Yakusuki, and Malcolm Eneri. So I hope to write about it shortly. It turned out to be more interesting than I was expecting. So I hope to have opportunity to discuss that with you sometime later. But so this actually leads to some interesting. Yes.
Sorry, before you go on, can you tell us a little bit about the argument, how you prove this?
Yeah, so well, we have two sets of argument, and so one involves the existence of interface. So you can actually this part we are actually more or less complete. So if you assume that there is actually a continuous there is an interface connecting CFT at lambda and lambda plus delta lambda, then you can actually reconstruct O. Okay. But there is actually a little bit but that's sort of more or less assumes the premise of conjecture zero, because what conjecture zero means that you can actually locally deform lambda. And that's almost the same as assuming existence of interface. But actually we are more ambitious, and actually we have an idea of how to prove this without assuming existence of interface. And so that's a part we are trying to actually complete. But yeah, and we are sort of halfway toward doing that. So, okay. And so of course, if you assume Lagrangian description, then it's obvious. But the question is that, well, not all the CFTs have obvious Lagrangian description. So that's sort of one of the reasons. Now, so this leads to some interesting connection with other conjectures. So of course, the notion of global symmetry has been greatly generalized for the last decade, starting with this generalized symmetry paper by Gaiotto, Kapustin, Zyberg, and Willett. And so in particular, absence of parameter in quantum gravity can be regarded as absence of -1 form symmetry. So this in some sense unifies some of the conjecture. So for example, I talked about absence of arbitrary parameter, but there is also no global symmetry. So this can be in some sense unified by regarding absence of arbitrary parameter as absence of -1 form symmetry. So this is actually one of the important insights of this cobordism conjecture by Jake and Kumran. And so this leads me to, of course, question, well, so as a more sort of refined version of this conjecture can also be related. And this weak gravity conjecture is in some sense sharper than distance conjecture, because when Kumran and I originally proposed, there was an order one leeway in this exponent alpha. But in the case of weak gravity conjecture, there was this sort of precise coefficient that people have figured out over here. So if there are also connections between them, that would be very interesting. So this was sort of partly motivated me to go on to the current project that I would like to share with you. Maybe I should I should make sure that I am keeping time. So I think I'm okay for now. The problem with this conjecture zero, that absence of parameter, is that this in some sense is not very useful because it doesn't provide a useful constraint on low energy effective Lagrangian, because what appear to be parameter in low energy theory may be fixed by potential in a more fundamental high energy theory. So for example, the standard model of particle physics has 19 parameters, or if you add the massive neutrino, if you take into account the mass of neutrinos, there are 7 more parameters. Or lambda CDA model of cosmology has 6 parameters. But they do not contain dynamical field corresponding to these parameters, at least in their low energy effective action. So I think the possibility is that there are indeed corresponding dynamical field, but those are fixed by potential in high energy, for example. That's a possibility. So Kumran and I in 2006 made two more, and in fact more than two, but I'm talking about these two based on string theory construction. So our idea is that only parameter space, or the parameter space, namely the moduli space of gravitational theory, there are always infinite distance direction. So in this case, distance is measured by the kinetic term defined, the metric defined by kinetic term of the field corresponding to parameters. And for example, in the Calabi-Yau compactification, there is this infinite distance direction.
Probably you mean if the marginalized space is not zero dimensional or something.
Sorry?
Probably you want to say if the marginalized space is not zero dimensional, like M theory.
Right. Yes. So if there is a continuous parameter, there is an infinite distance direction. I think that's what I should have. Is that what you wanted me to say?
Yes.
Okay, good. And another thing is that as you go infinite distance, the low energy effective.
Hi, sorry to interrupt. Just on this point, one more question. Like here you have in mind only Einstein gravity theories or
in all my distance conjecture statement I'm talking today, I'm assuming that the low energy effective action has a description in terms of weakly coupled Einstein gravity coupled to a finite number of matter field.
Because it's interesting that like the second part, like the one of the emergent tower of light particles seems more general, even if there is no Einstein gravity description, while the first one counterexamples, even if, I mean, if it's not an Einstein gravity description. No? So one could be more general than the other one.
Okay, I see. That's interesting. I haven't. I think so. Some of the assumption can be weakened. Yes. And another is that
what counterexample, Irene, do you have in mind for the other one? I'm curious.
The 3D compact conformal manifolds that are
but they are not. You're assuming that there is some gravity associated.
Yeah, if there is an AdS dual, but that AdS is not Einstein, right? In that case, it's compact, but still, I mean, we have examples which are non-Einstein and still have the tower whenever they are non-compact. So it seems that the existence of the tower is more general.
I don't think we do know whether every CFT has a gravity dual of some kind. That's what you're assuming?
If they have a large N limit, right? I mean, it's sort of we expect to have some gravity dual, but it's not Einstein necessarily if there is no a large gap.
Okay, yeah. So I misunderstood your question. So in some sense, in fact, I can make a stronger statement even for this because so in AdS CFT distance conjecture, at least the kind of things I'm going to present today is applicable for any unitary CFT with a gap, whether or not it has a weakly coupled gravity description. So in some sense, actually, I'm not going to prove this statement one, but in some sense, the spirit is that it can be applicable in a broader class of gravitational theory. So in fact, for example, it applies to some simple free sigma model with toroidal compactification, for example. Would that be in the direction of your question?
Yeah, it goes in the direction. I just think that, for the second point,
I'll present
for the first one, half.
I will present my statement and derivation, and you'll see that it can be applicable to broader class of theories. Okay. And but important thing is that also the second point, which is that as we go to infinite distance, low energy effective theory is broken with the emergent tower of light particle. And so we'll discuss some of these features in a sort of context where whether or not gravity theory in AdS has weakly coupled gravity description. But we make some assumption about CFT. Okay, so this is a distance part of the distance conjecture that Cameron and I proposed, and the first statement, this conjecture 2 and 3 are sort of precise version of the statement that I described over here. So there is an infinite, conjecture 1 says that there is always an infinite direction if there is a continuous parameter, and the second statement is that there is a tower of light particle emerging if you go in that infinite distance, the exponential minus alpha phi. And this has been tested by many examples, and some of you are here. And so Wolfgang is here, Dieter is here, and they studied this in a variety of examples. And then they can impose sharp constraint on as opposed to conjecture zero. They can impose sharp constraint, especially if this alpha is constrained. That it can be bounded. So that's what I would like to do. Okay. So talking about distance conjecture, I cannot resist mentioning this. So Inspire, this is Slack paper archive, occasionally has a tweet, or what is called tweet, the post on the X. And so they had some interesting post about my paper with Kamran in 2006. So they pointed out that for the last 10 years after we put it out, it was hovering like 10 a citation per year or so. So it's kind of one of the very low cited paper. But then around 2014 or 16, it whooped up. And they say that this paper is a sleeping beauty. And so you can ask, well, what happens around this time? And one of the things that happened was that the BICEP announced that it has detected the trace of primordial gravitational wave. And so this was interesting. This is a paper by Marco and Irene, but they pointed out that if distance conjecture is applicable in the context of inflationary cosmology, and if alpha is of order 1, then it gives you a very strong constraint on the tensor scalar ratio. And in particular, if the tensor scalar ratio is 0.2, then the theory is inconsistent. And but BICEP2 announced that the tensor scale ratio is exactly 0.2. So in fact, I was the deputy dean of physical science at Caltech around the time, and the dean told me about the discovery a month before the announcement, and he said, "Well, do you know what R is?" And he said 0.2, and I told him, "Well, then it kills string theory." But it wasn't the string theory that was killed. In fact, it was a BICEP which was dissected by astrophysicists like David Sparger. So I think this partly contributed to sort of increase of interest in this conjecture. So there is actually, so what I would like to discuss is a CFT version of this conjecture. So the moduli space of gravitational theory in anti-theta space is dual to conformal manifold in conformal field theory. So you can state the distance conjecture in the language of CFT. So there are two conjectures. The first two conjectures are like that. All point with higher spin symmetry at infinite distance. And another conjecture is that all CFT at infinite distance are higher spin point. And in fact, very nicely, this conjecture 1 was proven for supersymmetric theory already in the original paper. And for general CFT, it was proven by Bohm and Calderon Infante in 2000, last year. And but in this work, the constraint on alpha was not known. And so I was interested to go on and understand whether we can put any constraint on alpha. And Ifan Wang and I were able to do that, at least in the case of AdS3 CFT2. So that's the main thing I want to tell you today. So what we showed is actually part of this distance conjecture, which says that if there is a geodesic on the conformal manifold along which conformal dimension delta vanishes in some limit, then the Zamolodchikov distance to the limit is infinite. And then in that limit, the delta vanishes exponentially like this. And then we can put constraint on alpha. So there is upper bound on alpha. But we can also put lower bound on alpha. And so we have the alpha is actually sandwiched between 1 and 1 over square root of the central charge. And we also show that these bounds are sharp in the sense that we have identified the necessary and sufficient condition for saturation of this bound. And then we have identified actually theories which saturates the bound. So these are sharp bound. So basically this is what we showed, that if there is a point where delta vanishes, then it has to be at infinite distance for conformal manifold of 2D CFT, and alpha is bound like that. Now you can translate by using the dictionary of AdS CFT to this statement to the mass of the particle in the bulk, if there is a weakly coupled gravitational dual. And so you can write the mass square of the corresponding particle, the particle corresponding to this primary field with conformal dimension delta in this formula. And then this alpha can be bound between Planck scale and AdS scale. So you can see in particular that alpha is bound below by the Planck scale, which means that in the what it means for the scalar field phi is that if the scalar field phi goes beyond the Planck scale exactly by this numerical factor, then the tower of light states start emerging. Okay, so in the previous, in this nice work by Marco and Irene, they postulated the value of alpha and then derived this bound. But at least in this case, we can actually put precise numerical value to alpha. So that's sort of one of the interesting things. Of course, this is in the context of AdS3, but I hope that something like that can be done for higher dimension and eventually in flat space. Another interesting observation is that if you look at this, this S is the spin. So in particular, if S is 0 for scalar field, actually mass square goes to negative from the negative, go to 0 from the negative direction. So where in AdS, scalar field can have a slightly negative mass square. So in this case, actually the mass does not go down from the top, but it's actually come up from the negative mass square to the massless, but it's accumulate anyway. So at the mass equal 0, so in fact there will be an infinite tower. So it's true that low energy effective theory is broken anyway because there appears the infinite tower, but the way it appears is slightly different. So -1 happens when you take alternative quantization to the massless scalar field. Okay, so with yes.
Can we ask one more thing?
Sure, please.
I wanted just to make sure if then there is no scalars that approach the zero bound from above, all of them approach from below?
Well, so if you take the ordinary quantization, then mass square approach to some other value. And so there is a quantization of a scalar field for which mass square accumulates to some finite positive mass square. And then there is an alternative quantization where mass square approaches from negative and goes to 0. Okay. Yeah. So this is the precise statement is discussed in my paper with Ifan, but that's what happens.
And Hiroshi, have you tried to compare these bounds with the bounds you would expect from the emergent string conjecture? Like
yeah. So that's next slide. So you anticipated what I'm going to say. So in fact, well, so you can compare that with what's known, and in the appropriate flat space limit where you keep Planck scale and take AdS scale to be infinite, then this lower bound coincides with sharpened distance conjecture, but in 6 dimensions. So suppose, for example, you consider AdS 3 times S3 times K3 and take the limit of large n, then you get 6 flat dimensions. And then you can compare this inequality with that 6 flat dimensions, and it coincides. And so that's the true statement. And you can see that this is actually stronger than the constraint by this factor, 2/3, square root of 2/3. And so if you assume supersymmetry, you have a stronger constraint, and that stronger constraint coincides with the emergent string conjecture or sharpened distance conjecture. It's the same thing, I think, in the decompactification limit of AdS 3 times S3 times compact space, for example. Okay, is that the answer to your question? Okay, yeah. So it's nice that it's actually coincide with what's already known, and so this suggests that maybe this is actually the appropriate flat space limit that we should take in order to understand what we mean by taking. So this is as expected, right? So you take AdS 3 times S3 times K3 and take the n goes to infinite limit, and then you go to flat space, and this is exactly consistent with this result. Okay. We have made a few assumptions about it. I think actually I already spent half an hour, so I should hurry up. The main assumption is that the 4-point function of light scalars are well defined in the limit, and everything else follows from that. And in fact, the first two statements even do not assume existence of local stress tensor. So that means that they are applicable also to surface defect in higher dimensions. And this statement 3 does not assume that there is the family of CFT is continuous. So it's actually applied to discrete family too. For example, the C-1 limit of minimal model has a feature that is predicted by the theorem 3 and 4. Okay.
Hiroshi,
But these are assumptions. So for the rest of the talk, I'm going to give you some examples and prove these theorems. Okay, so that's what I'd like to do.
can I add something, Hiroshi?
Yes, please.
About the assumption, do you need to assume that the 4-point function is well defined in the strict limit, so at infinite distance?
No. So it has a finite limit in the, yeah. You'll
Okay.
see that when I the way that I will prove the theorem. Okay.
Okay.
Okay, so a few examples. So if you consider a sigma model on torus, the target space in torus, the moduli space is two complex dimensions. One is a volume and B field on T2, and another is a complex structure. And then there are finite distance points, for example, the orbifold point. And it's a finite distance, so we do not expect the gap to disappear. And in fact, for example, in these 3 points, there is a 2/3 of gap. On the other hand, the large volume limit is at infinite distance, and you can see that the gap decays exponentially in the homological distance with coefficient 1. So in this case, alpha equals 1. So this is consistent with the upper bound. The Calabi-Yau sigma model is more interesting because there are more different types of singularities. So in quintic, for example, there is a Gepner point. So that's the same as Z5 orbifold point. So it's similar to this Z3 orbifold point of the torus example. So there is again a gap. And there is an enhanced symmetry, and this gap is saturated by some non-BPS operator. The conifold point is very interesting, and this is also something that Komran and I studied in 30 years ago, I think. So there actually the spectrum, the tower of states start coming down, and in the conifold limit there is a continuum, but continuum has a gap. So there is actually a gap of delta equal 1/2, and above which there is going to be continuum in the conifold limit. And the limit is described by Liouville model or SL2R over U1. And then this is consistent with the fact that the conifold point is at finite distance. But large volume limit is at infinite distance. And in this case, actually alpha is not 1, but 1 over square root of 6. And we'll see later why this is reasonable. Okay? And then I have one more example, but maybe I'll skip it. I just pointed out that these theorems turned out to be not true if in this particular kind of non-unitary example. So this is just to demonstrate that unitarity is important in proving this statement.
So Hiroshi, the delta gap equals to 1/2. What would be the mass in the bulk that would that correspond to?
Oh, okay. Well, I do not know. You can figure it out. Yes. I cannot tell you off the top of my head. There is some particular particle. Yes. You can use the formula.
Okay, thanks.
Okay. So first, let me first tell you that if there is a point, a point where delta vanishes, the distance to that point is infinite, and delta decays exponentially, and alpha is bounded 1. Okay. So how do we prove this? So let's first start with a case, a simplest case, when there is only one marginal direction generated by is actually marginal operator. Okay, so that's sort of a simpler case. So suppose there is some primary field, and suppose this is scalar, and with conformal dimension delta, and then as you move on the conformal manifold, delta changes by this renormalization group equation controlled by the 3-point function of OOM. And you can easily see that in order for distance t to diverge at a point when delta equals 0, then COOM should vanish at least linearly in delta. By integrating this equation, you see that this 3-point function should vanish at least linearly in delta. So we can actually make a stronger statement that this vanishes linearly but with coefficient 1 in this case. Correspondingly, if you integrate this equation, delta goes like exponential minus t. So this is alpha equal 1 case. Okay. So how do we prove this? Well, if you use global conformal symmetry, then you have this commutation relation. So that means that if you take derivative of this operator with respect to z, then you should get to some 1-0 form. So not 1-0 form, the form of this conformal dimension. But since you have this commutation relation, there is square root of delta. Okay, so therefore, the 3-point function of O and 3-point function J can be related with this extra factor of delta. So what you need to show is that this 3-point function of JJ bar M goes to 1 in the limit of delta goes to 0. Okay, so we'll prove this using crossing symmetry of the 4-point function. Okay, and so in view of time, maybe I'll just give you a simple but not so rigorous argument, and I have a more rigorous argument if there are questions. Okay, so let me give the simpler but less rigorous proof. So this proof goes as follows. So 2-point function have conformal, the O has conformal dimension delta, so therefore its 2-point function should be of this form. So therefore, if you take derivative of this O with respect to Z and use this definition of J, then you can calculate 2-point function of JJ, J bar, and JJ bar. So JJ and J bar satisfies this kind of familiar relation, and JJ bar has delta on the top. Okay, so I transcribed it over here. Now let's consider 4-point function. Okay, if you consider T-channel expansion, which means that you expand J and J bar, then you can use these 2-point function. And you see that the leading term is this one. But you can also have S-channel expansion where you cut this OP through this channel. So now the leading term is JJ bar, and it comes with delta. So it is an identity exchange. But you can also insert exactly marginal operator here. In that case, you get CJJ bar M square and this function. And then there are exchange of other operator, but you can show in the more rigorous argument that these are orthogonal to these things. So you can actually isolate these and compare. But then nice things to notice is that the functional form of Z, W, etc. for this exchange term and for this exchange term are exactly the same. And this vanishes, and all these are orthogonal to it. So it has to be that in the limit of delta goes to 0, J bar M square is equal to 1. So by choosing the definition of operator appropriately, you can say that J bar M is equal to 1. So therefore, delta vanishes exponentially with coefficient 1. Okay, so this is sort of rough idea of the proof. Now, this is not yet rigorous because you need to show that these dot terms are orthogonal to this. So there is a more rigorous version of this, which introduce some kind of projection operator to project out to the term corresponding to this. But in view of time, I'll skip it. I can answer a question about this if there is any. But this is a standard technique of conformal bootstrap. Okay. Now, if you have more than one marginal operator, then the same equation that I described here, CJJ bar M square is equal to 1, becomes this equation. Now, instead of just one term, you have sum of these marginal operators equal to 1. Okay, and so then, so some of these operators may be marginal, but not exactly marginal. Some are exactly marginal. So if you even further project it down to exactly marginal direction, the sum of this 3-point function square becomes less than 1. Okay, so that's the origin of inequality. And another origin is that you may be going in the direction that is not optimal, and that may reduce also the value of alpha. So taking that into account, you can see that the delta, as you go into the particular infinite distance direction, then delta vanishes exponentially, but now the coefficient can be less than 1. Okay, it's bounded above by 1 because of this equality. Okay, so that's sort of the derivation of the first two theorems. That if there is a point where conformal dimension vanishes, distance to that point is infinite, and the approach is exponential. Okay, any question? Okay, so let me move on to the derivation of the other two bound, which is that the CFT in the limit is a direct product of sigma model in the large radius limit and some compact CFT. I will clarify what I mean by this direct product later. And the second statement is that there is actually lower bound, and the lower bound is 1 over square root of the central charge. Okay? So, so far I focused on some particular primary field whose conformal dimension vanishes. But in general, there can be several primary fields whose conformal dimension vanishes simultaneously. I'm not going to make any assumption about whether there is only one or whether there are several or there are infinitely many of them. It will turn out that there will be infinitely many of them. But well, at any rate, let's suppose there are some number of them. The number may be 1. Okay, but for each one of them, you can define this J just like we did in the earlier part of the proof. But this J may not be linearly independent in the limit. Before you take the limit when delta goes to 0, ONs are all linearly independent primary field. So therefore, JNs are correspondingly all linearly independent. But they may degenerate to become a same operator in the limit. So in case that happens, we want to find out whether there are any relation between them. So what kind of relation can we expect? The only relation we know operatorially among O's are operator product expansion. So we postulate there is an operator product expansion like this one. Now, if you look at this, in general, on right-hand side, there are a variety of operators that contribute. Some of the operators may also have conformal dimension vanishes, but some may have finite conformal dimension. But if those operators whose conformal dimension remains finite, their contributions are suppressed by in the limit when z goes to w, because these can become more singular. So we can focus our attention to the kind of field whose conformal dimension vanishes. So in some sense, this makes some kind of closed operator product expansion in the limit when delta goes to 0. Okay, and then by focusing on this type of operator, we can actually derive a variety of relation between J's. So let me go through that. So suppose, let's start with this operator product expansion and ask derivative operator with respect to Z and with respect to W and sum them. And take the limit when delta goes to 0, then you get actually this kind of linear relations. So that's nice. You can actually derive this linear relation. So if this linear relation is non-trivial, if the central operator product coefficients are such that this relation is non-trivial, then there is a linear relation. You can also derive quadratic relation, because suppose I take derivative with respect to Z and W, then you can actually find the relation that product of J's give you something that is linear in J and constant. Okay, but this looks like Kac-Moody algebra, current algebra relation. Okay, and so there is a linear relation and there is a Kac-Moody type relation. So you can see that by choosing appropriate orthogonal Hermitian basis of these operators, by sorting out this linear relation, you can organize this relation into this form. This is determined uniquely by the consistency of the algebra, where J's are now, curly J's are now linearly independent operators, and there is a quadratic term and there is a F term. Okay, I normalize J so that this coefficient is 1, but you can also introduce some level of algebra. But then unitarity requires that F is either 0 or has to be the structure constant of one of the compact Lie algebra. But if it is not non-abelian Lie algebra, then there is a gap. But the assumption is that gap vanishes in the limit, so we can exclude the possibility that F actually is non-trivial. So in order, at least for the sector where the conformal dimension vanishes, the structure constant has to be 0. So this leads us to this simpler current algebra. But if you have this, you can bosonize it. And then by the standard argument, you can see that all the operators whose conformal dimension vanishes should be on this vertex operator form. And this P takes discrete value for finite delta, but become continuous in the limit of delta goes to 0. So this shows that the conformal field still in the limit contains a subalgebra of local operator described by sigma model of Rn. But if you have a sigma model of Rn, that sector has a conformal central charge n. So that means that n has to be less than c, the original central charge of CFT. Now, so this means that this says that the CFT in the limit is locally like a sigma model with flat target space times compact CFT. But I do not want to say it's actually a direct product because there are non-trivial examples where it's not a direct product. So let's consider, for example, the sigma model whose target space is Z2 orbifold of a circle. So in this case, the operator whose conformal dimension vanishes is of this type, where R is the radius of this circle, and we take the limit where R goes to infinity. Okay, it has to be cosine because it has to be invariant under Z2 action. Z2 action flips the sign of X. So now if you use this definition of J here, and then calculate what this is, it is not del X, but del X multiplied by the sine function. Well, you can say that you may say that well, this operator becomes trivial in the limit of R goes to 0, infinity, but it's actually not. In fact, I can say that this O is actually a topological operator at the end of topological defect lines that implement quantum Z2 symmetry. So this is a famous paper by Qumran in the late 80s, I think, where if you have orbifold of some finite group, then the orbifold theory also have a new quantum version of the finite group symmetry. So in this case, the original theory has a Z2 global symmetry. The original sigma model has Z2 global symmetry. If you gauge that Z2, then you get orbifold theory, but the orbifold theory has quantum Z2 symmetry. So in that theory, the twisted sector, there is non-trivial Z2 action on twisted sector. And there is a topological defect line corresponding to that. And O tilde that defect line is endable, and endpoint is described by this defect, this operator. So this remains a non-trivial operator. So you see that in this case, they do not decouple, but del X actually has to come with some topological operator. There is also very interesting work by Mazel, Sander, Wan and In that appeared earlier this year. So they revisit the earlier observation by Runkel and Watts that you start with this minimal model whose central charge is 1 minus 6 over k times k plus 1, and it takes the k equal 1 infinity limit where you get c equal 1 CFT. Okay. So Runkel and Watts observed that this theory seems to contain something like sigma model whose target space is R, but there was something funny happening. And this new paper, they pointed out that actually the target space has a wall with interesting tachyon and dilaton profile. So it's locally like flat space, but there is some kind of global structure that is different from flat space.
Is that the same thing as the Landau-Ginzburg description of it, which suggests you have a field which is phi to the k? As k goes to infinity, you have or phi to some power. So, and as it goes to infinity, the only region that gets finite is within radius less than 1. Otherwise, it's infinite.
Yeah. I think it's very suggestive, and I suspect it's possible to refine, carefully look at this Landau-Ginzburg description to reproduce their result. This paper by Mazel et al. Derived this using string field theory. But I strongly suspect that there is a Landau-Ginzburg type explanation of the same phenomenon.
Yeah, that's basically what Zamolodchikov showed, that the minimum models are given by the Landau-Ginzburg models. So
right, so for finite k it is. And then I suspect if you take careful k
yes. Right, yes. Exactly. So phi to the k potential vanishes because for any region phi less than or equal to 1 in absolute value,
the potential becomes very flat, but then
infinite. Yeah, so therefore it follows.
Yeah, so I think that what you need to do is to carefully look at what happens in this region. And
and yeah, it's consistent with Zamolodchikov.
Yeah, I think it's consistent with what Zamolodchikov observed many years ago. Yes, I agree with you. And okay, so what I'm so here I was identifying what is a marginal operator, and using that we can derive this lower bound. So this is how we derive this upper and lower bound on alpha. And with super conformal symmetry, the lower bound can be strengthened, and that leads to this sharpened distance conjecture. So this also explains alpha equal 1 over square root of 6, because in quintic Calabi-Yau, C equal 9, and so this lower bound for superconformal theory exactly is saturated by quintic Calabi-Yau. Okay, so if CFT has holographic dual, we have shown that we have this inequality. So the tower of light particle must emerge with this one. So if you come up with any interesting theory like inflation theory, but this is negative cosmological constant, but it's different. But supposing something like that true in flat or accelerating universe, then having this kind of numerical constraint is very interesting. So I'm running out of time, so I'm actually over 5 minutes, so I apologize. So summary is that we have derived this statement that in two-dimensional CFT, the conformal dimension vanishes only at infinite distance, and the approach to the distance is exponential with this kind of bound. And more broadly, this shows that there are indeed constraints on low energy effective theory of gravitational theory that cannot be captured by the standard Wilsonian paradigm. So this is what Qumran proposed in 2005. And this is actually the sort of one of the existence proof that such constraints do exist and inevitable. And there are interesting line of absence of arbitrary parameter and global symmetry, which leads to this distance conjecture. I think we'd like to understand the connection better. And so more precisely, I'd like to prove or falsify the converse statement that the spectral gap always vanishes in the infinite distance limit. And so this beautiful paper by Bohm and Calderon Infante had a generalization to higher dimension, but no bound on alpha. So actually, I'm working with my student to try to generalize this, our result to higher dimension. There are lots of technical issues that we need to overcome. In my original conjecture 2006 with Qumran, we also had a constraint on topology of conformal manifold, and so it'd be interesting to understand the connection. And there is also a connection to weak gravity conjecture because you can think of absence of global symmetry, absence of a parameter as absence of -1 symmetry. So, and in fact, the existence of exactly marginal operators that we postulated and I'm trying to prove can be stated as splittability of -1 symmetry. So I think there is a deep connection, and of course, going to flat space and accelerating universe is an outstanding question. Okay, well, thank you very much for your attention.